In some Hilbert vector space H, let's consider some non-zero vector x. The inner product of x by any other vector is a scalar. This allows us to define a linear functional fx, defined by x. A functional is a thing which takes a vector as an input and returns a scalar as an output. The action of our functional is this. For any vector y, the action of fx on y is inner product of x and y. One can easily see that the functional defined like this is linear. The set of all linear functionals over H also forms a vector space. This space is called the conjugate space of H. We will denote it as H star. So, H is some Hilbert space, and the vectors of this space we place in these Dirac's brackets, called kets. H star is a conjugate space of H, and it consists of linear functionals over H. And the elements of it we will place again in these brackets, but reversed, called bras. The words bra and ket together form the word bra-ket. That's where these strange names come from. So the linear functional defined by vector x will denote as bra-x. And the action of this functional on any ket y, which is dot product of x and y, will denote as this, bra-x, then ket y, with the shared line between them. This, from now on, will be our notation for the inner product of two vectors. We remember that kets are represented as column vectors. It's time for us to define how we will represent bras. And it is very natural for us to represent them as vector rows with conjugated coordinates. Why? Because if we represent them like this, then the dot product becomes for us a simple matrix multiplication of a row and a column. So let's repeat what we just learned. First, for a Hilbert space, its elements, vectors, we denote as kets. These can be elements of the state space of some quantum system. So the state of a system in its state space is denoted as ket. Second, for the state space H, we can define a conjugate space, H star. It consists of linear functionals over H. We can construct those functionals with vectors of H. The action of such functional is inner product of its forming vector by vectors from H. For the finite-dimensional spaces, which present the particular interest for us, the whole space H star is constructed this way. This means that for any linear functional f, there exists a ket which defines f as an inner product by this ket. Third, the elements of H star are denoted as bras, and we choose to represent them as vector rows with conjugated coordinates. This representation allows us to define the inner product of vectors x and y as a matrix multiplication of row bra-x and column ket y. Vector row bra-x is called the Hermitian conjugate of the vector column ket x. So we are almost ready to introduce the new operation called the Hermitian conjugation. For now we know how this operation acts on scalars and vector columns. For any scalar alpha, the Hermitian conjugate of alpha is just alpha conjugated. For any ket x, the Hermitian conjugate of it is Bra-x, which is a row vector with conjugated components. And for Bra-x, its Hermitian conjugate is, by definition, ket x. So, as you can see, the operation of Hermitian conjugation, if performed twice, returns us the initial value. Let's see what else can we define to apply this new operation to.